Okay, it's my pleasure to introduce Marco Linton, and he's going to talk about the relation lifting and relation gap problems.
Great, thank you. Thank you for inviting me. So yeah, today I'm going to talk about the relation lifting and relation gap problems. So yeah, if you have any questions at any point, feel free to stop me. I'm very happy to answer questions. So let's see. There we go. So today I'm going to talk about the relation module. Essentially, this is what the relation gap and relation lifting problems are about. So in the first part of the talk, I'm going to describe what the relation module is, how to maybe go over some examples of different computations of relation modules. Then I'm going to talk about the relation gap problem, say what it is, give some motivation and some background, some history. I'll do the same for the relation lifting problem. And then at the end, I'll go over results, so known results due to other people, and then some new results, which should be on the archive very soon. Right. So, okay. So for me, a presentation is going to be essentially a free group and a normal subgroup of this free group, such that the quotient by this normal subgroup is the group G. Okay. And I'm very interested in this quantity. So this quantity is the smallest number of elements which you need to normally generate n. Usually this quantity is very difficult to compute. It sort of tells you the smallest possible number of relations you need to present your group on your fixed generating sets. So for, let's say, finely generated abelian groups, there is a nice formula where you can compute this quantity. And yeah, you can just use the rank of the first homology group and the second homology group of your abelian group to compute exactly what the rank of this. Well, you also need the number of generators to compute exactly this normal normal rank of the normal subgroup presenting your group. But then as soon as you move away from abelian groups, things get much harder. So, for example, there's this group which Epstein studied, I think in the 60s, which is just a free product of two fairly simple abelian groups. So you just take Z mod 2Z times Z, free product with Z mod 3Z times Z. And the obvious presentation where you have these two commutators and these two power relations, well, there are four relations. So the obvious guess you might have is that this is normally generated by 4 elements. Okay, so that's an upper bound. But is it possible that it's normally generated by 3 elements or 2 elements? This is an open problem, and we don't know the answer to this. And if you get bored during the talk, you can try and find normal generating sets for this normal subgroup. And at some point, I'll talk more about this group and why it'd be interesting to find smaller normal generating sets than the one I've given you here. Okay, so that's the presentation. So to talk about the relation module, I'm going to need to talk about group rings and modules over the group ring. So just to remind everyone, or yeah, what the group ring is, well, it's just a ring where consisting of elements which are finite formal sums of elements in the group times some integer, essentially. So all but finally many of these coefficients ZG have to be 0. And then you can replace Z with any ring you want, and then many of the things I'll say in this talk will be valid if you change Z for, well, most rings. So you can just bear that in mind. So, okay, we have a ring. Now we want a module, and if we want a module, we want an abelian group. And the natural abelian group to take would be the abelianization of this normal subgroup, which presents our group G. So that's what we're going to do. Now we need an action. Well, the free group acts on this abelian group by conjugation. We can extend this linearly to an action of the group ring of the free group on this abelian group. And because n acts trivially on its abelianization, then this action also descends to an action of the group ring ZG on the abelianization. Okay, and this module with the left ZG action is called the relation module. Okay, so they should put a warning here. For me, all actions are going to be on the left. I know often people consider conjugation a right action, but just bear that in mind. For me, everything is acting on the left. Okay, but you could equally make the relation module a right module by making it act on the right. Okay, so that's the relation module. I'm going to do an example, maybe give you another way of thinking about the relation module. So if you take your free group, which quotients onto your group G, and you take some free generating sets, then the relation module can also be seen as the group of cycles in the Cayley graph for your group G over this generating set you chose. Okay, so for example, let's take the Cayley graph of the free abelian group of rank 2. Okay, so this is a one-relator group. You have two generators, A and B. And on the right, there's the Cayley graph. I've only put 2 arrows, but you should imagine everything pointing to the right and pointing up. That's the orientation I've put on the one cells. And the normal subgroup N is actually the fundamental group of this Cayley graph. And so the abelianization of N is the group of cycles of this Cayley graph. And you can represent all these cycles by sums of one chains which have trivial boundary, so there's a picture. In the picture there's the red lines. They're part of some one chain, some elements in the relation module, and you can express this as this product here, which I've written here. So remember that this is a module with a group ring action. So the elements to the left of the dot is an element in the group ring, 3 times A inverse plus B minus 1 minus AB inverse. And this is acting on the left on this sort of generator, which is the commutator between A and B. So this 3A inverse is this cycle here where you have labels by 3, 3, minus 3, minus 3. Because we're translating sort of this commutator down through A, that corresponds to conjugating by A, and you go around 3 times. Okay, and then you can figure out why this is the correct expression for this element of the relation module. Okay, so we had this quantity which tells you how many generators you need for the relation. For the normal generators you need for N. You can also define a sort of rank, ZG rank of the relation module. And it turns out this is much easier to compute than the normal rank of the presenting subgroup. And this gives you a nice way to bound from below the normal rank of N, because just taking any set of normal generators of N and looking into the quotients in the abelian group, this gives you a ZG generating set for the relation module. Okay. So now we have a module, and we can compute. Let's say we can compute the rank slightly easier. Does this help us? Well, we get a lower bound. That's good. But we still not necessarily going to get equality. So that's what the relation gap is about. So I'll get to that in a second, but let's have a look at some examples of relation modules of groups. So one of the first examples that I know of is this theorem of Linton. It's called Linton's identity theorem, and it goes back to 1950. So Linton proved that if you have a free group and you take a single element in the free group and you quotient by its normal closure, this gives you a one-relator group. And Linton proved that the relation module of this guy is isomorphic to the group ring of the quotient group when W is not a proper power. So when W is a proper power, he also computes the relation module, but just for simplicity, I'm doing this case. But in this case, it's a nice free ZG module. It's just a cyclic ZG module. Okay. Another example of a computation would be this result of Cohen-Linden from the 60s. So if we have some small cancellation presentation, C prime 1 over 6, and we're not allowing any of the words to be proper powers either, then the relation module is going to be, well, similar to Linden's identity theorem, is going to be if you only had one relator, it'd be the same. If you have more relators, then you'll have a sum of Z copies of ZG, and the generators will correspond exactly to the generators of the normal generators of n that you started off with. So in particular, this gives you an equality, right? Because you had some normal generators for n, which was your sort of candidate for the best possible presentation, and we have this lower bound from the coming from the relation module. And if the relation module is this free module which realizes this quantity n, then we know that this is actually the best possible. Okay. And another computation which may be surprising, but maybe I led you to this. So is this theorem of Grunberg and Linnell from 2007. So this is the Epstein group, which I mentioned at the beginning of the talk. They computed the smallest number of ZG generators needed for the relation module of this free product of two abelian groups, and it turns out to be 3. So we had our guess, which was 4, and the lower bound is now 3. So there's still some space in between these two. Okay. And that's what the relation gap problem is about. So the relation gap problem asks, well, if you have a presentation of a group G, is it true that the two quantities, so the rank of the relation module and the normal rank of the presenting subgroup, are they always equal? Okay. So here I've sort of snuck in the hypothesis finally presented. And I'll say why we have to add finally presented. And that's because there are counterexamples to the version of the question where you don't ask for the group to be finally presented. So if G is not finally presented, well, okay. So let's say a definition first. So if F is finally generated, then the quotient group G has type FP2 over Z precisely when the relation module is finally generated as a ZG module. You can take this as the definition, or if you've seen a definition which is different to this, it's equivalent to this one. And for a while, it was an open question as to whether there existed a group of type FP2 over Z, which was not finally presented. So the first sort of results in this direction were due to Bierry and Strabel in the 70s. So they proved if you have a field K, so you can make this definition with any ring, not just Z. You just tensor the relation module with your ring R, or K in this case, and then you want this sort of relation module over this ring to be finally generated, and that's the definition of being FP2 over that ring. So Bierry-Strabel proved that if you have any field that you want, I think it's any field, it might have to be, no, yeah, any field, then they find examples of groups which have type FP2 over that field, but that are not finally presented. So that implies that there exists infinite relation gaps over fields. Okay. Doesn't answer the question because this is over a field, not over Z. But then 20 years later, Bespina-Brady came along and they have this wonderful construction where they find examples of groups which have type FP2 over Z, which are not finally presented. Okay, so this then gives you an infinite relation gap. The relation module is finally generated, so the quantity on the left is finite. Oops. The quantity on the left is finite, but then the normal subgroup cannot be generated by finally many elements. Okay, so this problem has yeah, I'll get to the origin in a minute. So, okay, in the 60s, T.C. Wall was interested in finding algebraic invariants of CW complexes to detect things like the CW complex being homotopy equivalent to a finite one, or to a finite dimensional one, or to, yeah, something of a certain dimension. And so he came up with this property Dn. There's one for each n greater than or equal to 2. There's also one for n is equal to 1, but it's slightly different, so I'm not going to mention it here. So property a CW complex X has property Dn if its ith homology group, the ith homology group of its universal cover vanishes for I strictly greater than n, and if the n+1 cohomology of, so here I'm taking I'm taking the chain complex of the universal cover and considering this as a complex of ZG modules. So if the cohomology over any ZG module M vanishes in dimension n+1. Okay. And it turns out that, well, it's a theorem that Wall proved in 65, that if you have a CW complex X and this CW complex X has property Dn, then it's actually homotopy equivalent to a complex of dimension n. Okay, this is an if and only if. So, okay, the definition is for n greater than or equal to 2, but the theorem is for n greater than or equal to 3. So that leaves some gap, right? So that's what became known as Wall's D2 conjecture. And the conjecture states that, well, if you have a CW complex X, which has the homotopy type of a two-dimensional CW complex, then that should be the same as X having D2. Okay, so how is this related with the relation gap problem? Well, it's a theorem of Dyer that there is a theorem of Dyer which allows you from a group presentation which has a relation gap, allows you to find a CW complex which looks like which has D2, but which does not have the homotopy type of a two-dimensional CW complex. And the conditions are, well, okay, you have a group G and you need the third cohomology to vanish, and you need the presentation that you realizes some sort of deficiency. So that's the deficiency should be the difference between the rank of the second homology group and the first homology group, where here by deficiency I mean the difference between the number of relators and the number of generators in your presentation. If that has a relation gap, then D2 is false. And okay, so I said at some point that I would give some reason why the question about Epstein's group was interesting. Well, here it is. If you can prove that Epstein's group does have a relation gap, then you get a counterexample to Wall's D2 conjecture. Okay, so then this is quite an old conjecture, and it seems like it's such a nice and simple group. One should be able to understand everything about it, and yet we still don't have a conjecture. And I should mention there are other very nice examples due to Brighton and Tweedale, which essentially do a similar thing. The relation module computations are perhaps more explicit, but the groups are slightly more complicated. And again, they also have this, if they have relation gap, then D2 will also be false. Okay, so that's some motivation for the relation gap problem. Are there any questions? Okay. Right. So that's the relation gap problem. So next I'm going to talk about the relation lifting problem. So this is a slightly more precise version of the relation gap problem. And this one was actually asked by Wall in 66, or rather an equivalent problem I'll explain why it's equivalent in a second. But essentially, this question was asked by Wall. So what's the question? Well, the question is, instead of asking for whether there's a gap, we want something slightly more precise. That is, given relation module generators, do these relation module generators actually come from normal generators of your normal subgroup? So this is a much stronger requirement than asking for there to be no gap in your presentation. We'll see in a second why it's much stronger. But so yeah, formally you have some set of generators of your relation module, and again we're assuming everything has finitely many generators. And the question is there some sets which of normal generators of n which project to these relation module generators? So on the face of it, I haven't added this finite presentability hypothesis. So immediately you might think, okay, what about the Bessvino-Brady examples? Yes, you'll be right. They would also give an example of groups which do not admit relation lifting. But I want to convince you that even though there are counterexamples to this statement, this is still an interesting problem. First, I want to give an example or a counterexample of a different flavor to this problem, and this was given by Dunwoody in the 70s. So the counterexample is a one-relator group. It has torsion. It's just the free product of Z with Z mod 5Z. And so just to show that this is quite subtle, because this is a one-relator group. The relation module is cyclic, so there's no relation gap in this case. But there is this element, which okay, I've written here, which generates the relation module, but which does not come from a generator of the normal subgroup, which is kind of mysterious. So what is this element? So this group has torsion. So the idea is Dunwoody is using sort of non-trivial units in the group ring of this group to sort of shift the standard generator of the relation module, which comes from a generator of the normal subgroup, to something which is, on the face of it, has nothing to do with your original generator, but this is just a product of conjugates of the generator. So if you did the exercise in the beginning, then this computation should be clear. So if you multiply by b, then this corresponds to conjugating by b, right? So then multiplying by a minus a b conjugates by minus a inverse b inverse. Oh, I think that's a typo. Anyway, exercises to fix this computation. So, okay, so why does this not lift? Well, there is this result of Magnus from I think it's the 30s, but I might be wrong. Which gives you an exact, it tells you exactly when an element normally generates a normal subgroup, which is already normally generated by a single element, and that is like all the normal generators are conjugates to each other or to their inverses. So this element here, this b a to the 5 b inverse, etc., this guy is not conjugate to a to the 5 or a to the minus 5. And a to the 5 is a normal generator of this normal subgroup. So in particular, this guy cannot normally generate n. But because this element on the left, this 1 minus a plus a squared times b, is a non-trivial unit of the group ring, this element here does generate the relation module, because you can just left multiply by the inverse of this unit and you get back to your standard generator. Okay, so there's no gap, but you can't lift, or can't always lift relations. Right. So why is this still interesting? So this again stems from work of Wall. So just some notation. So if X is a connected CW complex, and G is the fundamental group of X, then okay, the X tilde is the universal cover. Then the cellular chain complex of this universal cover is a complex of free ZG modules. And these ZG modules have their bases can be chosen to be in correspondence with ZG orbits of lifts of n cells in the universal cover. Okay, and so there's this lemma which I think I've mentioned in passing. So if you take the free group to be the fundamental group of the one skeleton of the CW complex, and N is the kernel of the map from F to this fundamental group, this gives you a presentation of the group. So this is like the two skeleton is sort of the presentation complex of the presentation that you chose. Then the image of this second boundary map, so from C2 to C1, this is isomorphic to the relation module over this presentation. Okay, conversely, you could take some chain complex, an arbitrary chain complex of free ZG modules. Okay, it's called A star, and choose some free bases in these free modules AI, so that the nth group, nth module is isomorphic to some free ZG module with basis coming from these Bn. Okay, and then the realization problem asks, well, okay, I have some chain complex. Well, when does this chain complex actually come from the chain complex of a CW complex, of the universal cover of a CW complex? And when do the basis elements actually correspond to basis elements coming from cells in the universal cover? And if this A star does come from a CW complex, then we call it realizable. So why might we be interested in realizability? Well, so there's this theorem of Wall, another one by Wall, which tells you essentially if you have a CW complex and you have a chain homotopy equivalence with some realizable ZG complex, then you can actually realize this chain homotopy equivalence by an actual homotopy equivalence of CW complexes, where this new CW complex has the chain complex isomorphic to A star. Okay, so this would be interesting, for instance, if you wanted to detect whether X was homotopy equivalent to a two-dimensional CW complex, because if your chain complex of the universal cover was chain homotopy equivalent to something which has dimension 2, then you know that your CW complex admits some homotopy equivalence to a two-dimensional CW complex. But there's this one caveat, which is you want this A star, this chain complex, to be realizable chain complex. And okay, I'm going to essentially tell you that this is essentially equivalent to the relation lifting problem, and so it's not always realizable. Nevertheless, if you can show that certain types of chain complexes are realizable, then you have a way of detecting certain properties of CW complexes just from chain homotopy equivalences of complexes. Okay, so there's some obvious necessary conditions you might need for your complex of ZG modules to be realizable. One is this being algebraic, which is really a collection of conditions. So a complex of free ZG modules is algebraic if, well, one thing is you need zero homology to be Z. Okay, that's just saying that the CW complex that you want it to be realized by is connected. The second is that the first homology vanishes. That's just saying that the CW complex, well, the universal cover of the CW complex is simply connected. Okay, and the other thing is that you want the basis elements in dimension 1 to sort of act like oneself, basically. So you want basis elements in dimension 1 to go to, some difference of 2 basis elements in dimension 0. Okay. Dimension 1 things are much, much easier. So that's one necessary condition. And if you take, so if you take any sort of, if you take any, let's say, presentation complex, then the chain complex of the universal cover gives you some sort of presentation of the augmentation ideal of your group ring. Right. So, so these are some necessary conditions. Sorry, yeah, I skipped ahead a little bit. So, so if you have some algebraic complex of ZG modules, then the image of this D2 map, this is actually the relation module of your group presentation, where the relation module, I haven't said what n is in this case, but you can construct n just from the conditions of this chain complex being algebraic. So then if this submodule of A1 is isomorphic to the relation module, then basis elements of A2 corresponds to generators of this relation module, because we had this condition that the first homology needs to vanish. So in fact, these relation module generators coming from this choice of basis elements in A2 being liftable is, so liftable meaning they come from normal generators of n. This is equivalent to this complex being realizable. Okay, so in dimension 2, relation lifting is the same as being realizable. But it turns out that in all dimensions, it's also this essentially the same problem, because Wall also proved that if you have some realizable complex in dimension 2, then actually the whole complex is realizable. Okay. I think, yeah, that's the end of the sort of motivation and background of these problems. So now I'm going to talk about results, so positive results and new results. So as far as I'm aware, these are essentially the only positive results which are not specific examples. So, and they're both due to Hollander from the 90s. So I think Jens is in the audience, so maybe you can correct me at some point. But so the two results which I do know are these. One is essentially saying that if you have an abelian group, then you never have a relation gap. Okay, for whatever presentation you have, the relation module generators give you normal generators of your group. And the second result is about groups with cyclic relation module. So Hollander proved that if you have a finally generated solvable group, which has a presentation with cyclic relation module, or rather the rank of the relation module is 1, then in fact the normal rank of the presenting subgroup N is also 1. So in particular, it's a one-related group. And because there was a classification of one-related groups, well, of I guess solvable groups of cohomological dimension 2, one can also deduce that actually there are only 2 possible families of groups that this G can be, which are cyclic groups or BS1n, where BS1n here is the Baumschlag-Solotar group, where you conjugate one generator to a power of itself. And as far as I'm aware, these are the only positive results. So I guess until this talk, which yeah, okay. I'm skipping ahead again. So okay, so Jen's proved this lovely result. And this, I guess, motivated the question, which is here. So if you have a presentation of a group which has a cyclic relation module, and the question is, does this come from a one-relator group? Is the presenting subgroup N normally generated by a single element? Well, okay, in general, probably the relation gap problem has a negative answer, but one could hope that maybe for low enough rank relation modules, that this would be the relation gap problem would have a positive answer. And well, Jen proved that there is a positive answer for solvable groups, and one of the main results of this talk is that if you have a group which is right orderable and the relation module is cyclic, and this is valid over any domain, not just Z, then actually your group is a one-related group. So N is normally generated by a single element. So I haven't defined what a right orderable group is, but essentially your group has an total order on all its elements, and it's invariant from multiplying on the right. So if A is smaller than B, then AC is smaller than BC. Okay, many groups are right orderable. If you know what a locally indicable group is, then any locally indicable group is right orderable. And more importantly, any torsion-free one-related group is an example of a right orderable group. So this applies to all one-related groups which are torsion-free, for example. Okay, I've stated a slightly more general version of the specific case where R is a domain and not just Z. And that's because, well, over R, there is no relation gap for right orderable groups, but it's not true that you can lift every relation module generator. So the precise statement is you can lift relation module generators, in this case, up to taking a root. So possibly there is a normal generator which has a power which is equal to your relation module generator you started off with. And I mean, the upshot of this is that when you only care about the relation module over Z, over ZG, then actually every generator of the relation module does lift to a generator, or a normal generator of N. Okay, so relation lifting is always possible amongst right orderable groups with cyclic relation module. That's the result. But this is this is really a corollary of a slightly more technical result, but I wanted to state the sort of the simplest version of it. So the more general result is really about the realizability of certain complexes. So if G, again, we need to assume G is a right orderable group, and we have let's take some algebraic ZG complex. So dimensions 2 in dimension 2. And the main theorem really is about types of maps that D2 can be. So if D2 is given by, so this is the map from A2 to A1, is given by a lower triangular matrix where all the diagonals are non-zero, all the diagonal elements are non-zero. So here, everything below the diagonal can be whatever you want, and everything above the diagonal is 0. Then this complex of ZG modules is realizable. And again, this is all true. Sorry, that's not quite true. So it's not true if one replaces Z by a domain R, but it's almost true if you replace Z by a domain R. Yeah, almost true. In the same sense that you could almost lift relations for in the R relation module in the cyclic case, but not quite up to proper powers. So this is some caveats, which I forgot to mention here, but essentially true if you replace Z by R. Okay, so this is quite this is fairly abstract. We've gone quite far away from CW complexes. I've just told you, okay, there's some complex of ZG modules and it's realizable by some CW complex. What does that really mean? What are the CW complexes that arise from such things? Okay, I guess the first comment I should make is that if this this matrix is a 1 by n matrix, then what does this mean? This means that the relation module, remember, which is the image of D2, is cyclic. So the result about cyclic relation modules is really sort of the n is equal to, well, okay, I've said the wrong integer, but so it's when the number of rows is equal to 1. Okay, so that makes these theorems corollaries of this theorem. Okay, so then what are the CW complexes that actually are realized by such complexes? Turns out that they're realized by CW complexes, which were studied by Howie in the 80s. And these are called the reducible complexes. So a 2 complex is reducible if it can be expressed as a union of subcomplexes xi, where, well, x0 is going to be the 0 skeleton, and for each I, xi plus 1 minus xi, it either consists of a single 1 cell, or it has 1 cell and a 2 cell, whose attaching map is, it's got to traverse this new 1 cell ei plus 1, but in a sort of essential way. So what do I mean by this? I mean, you can't homotope the boundary, the attaching map into a subcomplex of like lower down. So you can't freely homotope it into xi. Okay, so you can sort of imagine why this gives rise to these sort of lower triangular matrices, right? You're adding a generator and adding a relator, which sort of mentions this new generator in an essential way, and this should give you like rows where the previous generators don't mention anything afterwards, so you have zeros all the way along here, and this new relator at some point picks up something along this new generator, but doesn't mention any of the later generators, and so you get this lower triangular matrix. Okay, so what's the upshot? The upshot is if you have a 2 complex with right orderable fundamental group, then you can detect whether this 2 complex is homotopy equivalent to a reducible complex just by looking at the chain homotopy equivalences of the chain complex of the universal cover. So if there is a chain homotopy equivalent between C star of X tilde with a ZG complex A star, where the second map D2 is given by a lower triangular matrix with these non-zero diagonal entries, then actually X turns out to be homotopy equivalent to a reducible complex. The other direction, so yeah, one direction is new, and it's a consequence of the theorem on the previous slide. And the other direction is, essentially due to work of Howie from the 80s. I'm not sure I've seen the results stated in exactly these terms, but it's, yeah. So one direction is due to Howie, and the other direction is a consequence of the previous theorem. And so I should also mention that the theorem here, although, okay, because I've put the matrix, yeah, I don't want to give a technical definition. This theorem is also true if the matrix is not finite. So you could also have you need to change the definition appropriately, have some infinite matrix, and then this would allow you to detect whether your CW complex is homotopy equivalent to an infinite reducible complex. So that's why I put this finite in brackets. So particularly if you can find some A star where the AI are all finely generated, then you know that the fundamental group of X is actually a finely presented group. And it has a sort of finite reducible presentation. Okay, I think that was all I had to say. I think I rushed slightly, but yeah, that's all. Thank you.
Thank you very much, Marco. Are there any questions for Marco? Hi, I can't hear him. Can you guys hear?
I can't hear.
Okay, not me, only, yeah.
Okay, so maybe I can ask a question. So you have just the positive result for finally generated binning groups. So the next class of groups you can consider naturalist is finally generated and the potent groups. Any result on that? Does your new result imply anything about the class groups?
Yeah, it's a very good question. And the answer is I don't know. So I know there are papers on relation modules of two-step nilpotent groups, for example, but I don't think that anyone has actually proved that whether there's a relation gap or not. Sorry, whether there's not a relation gap for those groups. But yeah, it's an interesting question. That would be the next natural class.
I don't know if you can hear me now.
Yes.
Yeah, we can hear you now.
Now my headphones work. You know, with the nilpotent groups, there's an old result of Grünberg's, and if you look at a finite P group, then the relation module, the presentation from the relation module point of view looks balanced. So you can prove you need as many relation module generators as you have generators in the group. And so it's a good open question whether finite P groups are always balanced, have always balanced presentations. I think that's an open question. But Marco, if I could see your slide with your main result on this groups with cyclic relation module.
Yes, this one.
So it seems like one would think that these that your groups are locally indicable, just like one-relator groups. But I don't know in general, but there are probably scenarios where this is true. I mean, another way to look at these groups with cyclic relation modules is just as quotients of one-relator groups by perfect normal subgroups. And so I think if you can put conditions on the one-relator group, for example, of being an E group, and you quotient out by the maximal perfect subgroup, chances are that the quotient is locally indicable.
Well, in this case, all these groups in cyclic relation module, because they're going to be one-related groups, because when you're assuming right orderability, and so
right,
that will be locally
but
indicable.
I'm just saying how to get away from that assumption.
Yeah. So I mean, okay, that's another good point, because I also have this other paper where I compute the sort of maximal perfect subgroup, and so in that case, the maximal perfect subgroup is normally generated by a single element. In the case that the group is an E group and a one-relator E group, so then that quotient will also be locally indicable.
Okay, yeah.
But yeah, then the issue is that So you can look at the maximal perfect normal subgroup, but then once you kill that, you sort of lose all the information about the perfect normal subgroups contained in that maximal perfect subgroup. And yeah, without this assumption of right orderability, I don't really know how to get around that problem. But you can find examples of groups which are not one-related groups, but their relation module over the rationals is cyclic. So there are relation gaps over the rationals, even when the relation module is cyclic over the rationals. But this theorem is saying that when the group is right orderable, then there's still no relation gap even over the rationals.
Okay, so in your theorem 3, there's the small cancellation condition. So there are many generalizations of the small cancellation conditions. Are there any results on the more general small cancellation conditions?
So I know Macarena-Arenas proved the same, I guess let's go back to the theorem, the same theorem, but for C6 small cancellation condition. This was last year, I believe. So that answered a question of Linton, I think, not from this paper, but from another related paper, where he also asked about this. Well, so essentially the proof of this theorem and Macarena-Arenas' theorem is proving that the normal subgroup N has this Cohen-Linton property, which comes from this paper of Cohen-Linton. Because they managed to prove that these groups have this Cohen-Linton property. Obviously, they didn't call it that back then, but this property implied that the relation module had this particularly nice form. And so, yeah, Macarena-Arenas proved that this Cohen-Linton property holds also for C6 small cancellation groups. But other small cancellation conditions, I don't know. I think C6 was probably the best possible of the non-geometric conditions. Yeah, I'm not sure if there's any other conditions, but these two do give you this nice decomposition.
Okay, thank you.
Any other comments or questions? Okay, if not, then thanks. Let's thank Marco. Thank you very much, Marco, for joining us today.
Thank you very much.
Can I add something?